Welcome to the beginning of Chapter 12. This is our last chapter in Calculus 2, and we're looking at parametric and polar curves in this chapter. In section 12.1, which we're starting here, we're looking at parametric equations. Up to this point, we've focused our attention on functions of the form y equals f of x and studied their behavior in the setting of the Cartesian coordinate system. There are, however, alternate ways to generate curves and represent functions. We begin by introducing parametric equations, which are featured prominently in upcoming chapters to represent curves and trajectories in three-dimensional space. When working with objects that have circular, cylindrical, or spherical shapes, other coordinate systems are often advantageous. In this chapter, we introduce the polar coordinate system for circular geometries. Cylindrical and spherical coordinate systems appear in Calculus 3. After working with parametric equations and polar coordinates, the next step is to investigate calculus in these settings. How do we find the slopes of tangent lines, rates of change, areas of regions, and arc length, when the curves of interest are described with parametric equations or described in polar coordinates? The chapter ends with the related topic of conic sections, ellipses, parabolas, and hyperbolas, all of which are conic sections, can be represented in both Cartesian and polar coordinates. These important families of curves have many fascinating properties, and they appear throughout the remainder of the text. Parametric equations, the basic idea. Imagine a motorboat travels clockwise around a circular course with a radius of 4 miles, completing one lap every 2 pi hours at a constant speed. Suppose we wish to describe the points on the path of the boat, x of t and y of t, at any time t is greater than or equal to 0, where t is measured in hours. We make an assumption that the boat will start on the positive x-axis at the point 4, 0. Note that the angle corresponding to the position of the boat increases by 2 pi radians every 2 pi hours, beginning with theta equals 0 and t equals 0. Therefore, theta equals t for any t greater than or equal to 0. It follows that the x and y coordinates of the boat are 4 cosine t and 4 sine t, as you can see in the diagram to the right, where t is greater than or equal to 0. You can confirm that when t equals 0, the boat is at the starting point 4, 0. When t equals 2 pi, it returns to that starting point. The equation x equals 4 cosine t and y equals 4 sine t are examples of parametric equations. They specify x and y in terms of a third variable, t, called a parameter, which often represents time. So get that. Parametric equations specify x and y in terms of a third variable called a parameter, and the most common one is time. In general, parametric equations have the form x is a function of t, and so is y. It's also a function in t, where f and g are different functions, and their given functions, and the parameter t typically varies over a specific or a specified interval. For example, between a and b, that we saw in the last example. The parametric curve described by these equations consists of the point in the plane xy equals f of t and g of t for t between the interval values of a and b. And so you have a diagram here. So in general, what we have for functions is x is the input to a function f, and then y is some calculated function of with x as the input. But in a parametric description, t is the input, and then these functions f are a function to calculate the value of x, and the t input to a different function g is how we get the y values here. And so this is a kind of a diagram comparing a normal function description to a parametric description. Let's look at our first example. Graph and analyze the parametric equations x equals f of t equals 2t and y equals g of t equals 1/2 t squared minus 4 for 0 is less than or equal to t, and which is less than or equal to 8. So for t between 0 and 8. Plotting individual points often helps in visualize a parametric curve, just like in any other graph. Just plotting points, x and y values, and then plotting them on our Cartesian system can really help us see what's going on. Table 12.1 shows us the values of x and y corresponding to several values of t on the interval between 0 and 8. By plotting the pair xy pairs in Table 12.1 and connecting them with a smooth curve, we obtain the graph shown in Figure 12.3. As t increases from its initial value of t equals 0 to its final value of t equals 8, the curve is generated from the point 0, -4 to the final point 1628. Notice that the values of the parameter do not appear in the graph. The only signature of the parameter is the direction in which the curve is generated. In this case, it unfolds upward and to the right as indicated by the arrows. Sometimes it's possible to eliminate the parameter from a set of parametric equations and obtain a description of the curve in terms of x and y. In this case, from the x equation, we have t equals x over 2, which may be substituted into the y equation to give y equals 1/2 t squared minus 4, which equals 1/2. Substituting in x over 2 for t, we get 1/2 x over 2 squared minus 4, which gives us x squared over 8 minus 4. Expressed in this form, we identify the graph as part of a parabola. Because t lies in the interval between 0 and 8 and x equals 2t, it follows that x lies in the interval between 0 and 16. Therefore, the parametric equations generate the segment of the parabola for between the values of x equals 0 and x equals 16. Given a set of parametric equations, the preceding example shows that as the parameter increases, the corresponding curve unfolds in a particular direction. The following definition captures this fact and is important in upcoming work. A positive orientation. The direction in which a parametric curve is generated as the parameter increases is called the positive orientation of the curve, and is indicated by the arrows on the curve. So this doesn't necessarily mean that the slope is positive. It just is saying what direction does the curve go as the parametric variable, in the last example it was time, increases. Let's look at example 2, a parametric circle. Confirm that the parametric equations x equals 4 cosine 2 pi and y equals 4 sine 2 pi t for t between 0 and 1 describe a circle of radius 4 and are centered at the origin. Well, if we plug in values here, we get ordered pairs all the way around the circle that you can see on the diagram to the right. Plotting those points as t increases from t equals 0 to t equals 1 results in a graph that appears to be a circle of radius 4. It is generated with positive orientation. You can just barely see the arrows there, in the counterclockwise direction, which we remember back from trigonometry, beginning and ending at 4, 0. And that's this figure here. Letting t increase beyond t equals 1 would simply start the second revolution around the circle. To identify the curve conclusively, the parameter t is eliminated by observing that x squared plus y squared, which is equals r squared, which is the standard definition of a circle centered at the origin, if we substitute in the parametric equation for x and the parametric equation for y, notice what we get. We get 4 cosine 2 pi t squared plus 4 sine 2 pi t squared, which gives us 16 times cosine squared 2 pi t plus sine squared 2 pi t. Well, of course, by the Pythagorean theorem, the Pythagorean identity, cosine squared plus sine squared equals 1. So we get that this x squared plus y squared equals 16, which confirms that this is a graph of a circle with the radius equaling the square root of 16, or 4. Okay? So we're going to pull from some prior knowledge in trigonometry here to kind of help us map these things in the orientation as well. So now let's look at problem B. Suppose a turtle walks with constant speed in the counterclockwise direction on the circular path from part A. So now we have a turtle, and he's moving around this circle, and he's moving at a constant speed. He's starting at 4:0, and he completes one lap in 30 minutes. So now instead of t equals 1, we have t equals 30 minutes to go one revolution. Find a parametric description of the path of the turtle at any time t is greater than or equal to 0, where t is measured in minutes. So if we duplicate the calculations here, with any non-zero real number b, it can be shown that the parametric x equals 4 cosine bt and y equals 4 sine bt also describe a circle of radius 4. When b is greater than 0, we have a positive orientation going in the counterclockwise direction. And the angular frequency, which you might remember back from trigonometry again, it impacts the period, if you will, so that we have one revolution is 2 pi, unless we've adjusted the period. The angular frequency must be chosen so that as t varies from 0 to 30, the product bt varies from 0 to 2 pi. Specifically, when t equals 30, we've completed one revolution, and so we have 30b equals 2 pi. Notice we're substituting that in there. 2 pi is one revolution, so how long does it take to get around one revolution? That's 30b. So b equals pi over 15. Let me solve for b here. Therefore, the parametric equations for the turtle's motion, by substituting in a value for b, we get x equals 4 cosine pi over 15t, and y equals 4 sine pi over 15t for t between 0 and 30. You could check here to make sure that as t varies from 0 to 30, the points x, y make one complete circle of radius, and you can see some values plotted on there. Okay? So it's kind of interesting that we're pulling in these trigonometry identities and knowledge as we're moving into this parametric equations and using these in calculus. If we look at generalizing example 2 for non-zero real numbers a and b in the parametric equations, x equals a cosine bt, y equals a sine bt, we find that x squared plus y squared, which equals each of those terms squared, equals a squared times the product of the cosine squared and the sine squared, which of course equals 1, which then equals a squared. Therefore, the parametric equations x equals a cosine bt and y equals a sine bt describe all or part of the circle x squared plus y squared equals a squared centered at the origin with radius a. For any non-zero value of b, the circle is traversed once as t varies over any interval of length 2 pi over b. If t represents time, the circle is traversed once in 2 pi over b time units. That means we can vary the speed at which the curve unfolds by varying b. If b is greater than 0, the positive orientation of the parametric equations is in the counterclockwise direction. If b is less than 0, the curve is generated in the clockwise direction. More generally, the parametric equations x equals x sub 0 plus a cosine bt and y equals y sub 0 plus a sine bt describe all or parts of the circle x minus x sub 0 squared plus y minus y sub 0 squared equals a squared. So this is the circle that's centered at x sub 0, y sub 0 with a radius of a. If b is greater than 0, then again the circle is in the counterclockwise direction. Example 2 showed that a single curve, for example, a circle of radius 4, may be parameterized in many different ways. We went around the circle in different parameters of time and period, if you will. Among the most important of all parametric equations are x equals x sub 0 plus at, and y equals y sub 0 plus bt for t between negative infinity and infinity. And this is where x sub 0, y sub 0, a, and b are all constants with a not equaling 0. The curve described by these equations is found by eliminating the parameter. The first step to solve the equation, the x equation for t, which gives us t equals x sub 0 minus, x minus x sub 0 over a. So we're just solving this original parametric equation for t. When t is substituted into the y equation, so we're going to take this value and substitute it into the y equation, y equals y sub 0 plus bt equals y sub 0 plus b times the t factor defined in terms of x. Notice what happens here is we get y minus y sub 0 equals b over a times x minus x sub 0. This equation describes a line with slope b over a passing through the points x sub 0, y sub 0. Therefore, the equations x equals x sub 0 plus at and y equals y sub 0 plus bt for t between negative infinity and infinity, where x sub 0, y sub 0, a, and b are constants with a not equal to 0, describe a line with slope b over a passing through the point. So these parametric equations give us basically kind of what we used to think of in trigonometry as the equation of the tangent line. So this is the line going through x0, y0 with slope b over a. And so that's an interesting kind of proof of that and how you can take these parametric equations and come out with an equation of a line. Notice that the parametric description of a given line is not unique. For example, if k is any non-zero constant, the numbers a and b may be replaced with ka and kb respectively, and the resulting equations actually describe the same line, although it may be generated in the opposite direction and at opposite speed. So we're talking about using k as a multiplier on a and b. Let's look at example 3, parametric equations of lines based upon the definition we just went through. Remembering that x equals x sub 0 plus at and y equals y sub 0 plus bt are the equations of a line, and remember that the slope of that line is b over a. So we can figure these three problems out with that basic definition, and mainly using algebra and math that we know from before. So part A, consider the parametric equations negative 2 plus 3t and y equals 4 minus 6t for t between negative infinity and infinity, which describe a line. Find the slope-intercept form of the line. So here, to eliminate the parameter, we're going to do just like we did before. We're going to solve the x equation for t to find a value of t that we can then plug into the y equation and then rewrite it in the slope-intercept form of the line. So as we solve for t for in the x equation, we get x plus 2 over 3, which you can see here, and that's just doing the algebra to solve for t from the original parametric equation. We then plug that formula in for t into y equals 4 minus 6t, and plugging in x plus 2 over 3 in for t. And so notice we get 4 minus 2x minus 4, which simplifies to just negative 2x. Notice there's not a y-intercept, so that means that the line passes through the origin. So the line y equals negative 2 passes through the origin with a slope of negative 2. Okay? Notice in part B, we're given we want to find two pairs of parametric equations. We're given the slope, and we're giving a point that it goes through. Okay, remember x sub 0 and y sub 0 is a point on the line, and a and b are represented, b over a is represented by the slope. So we can use the general parametric equations that we see up here. And because the slope of the line is 1/3, we choose a equals 3 the denominator and b equals 1 the numerator, so we have b over a, 1/3. Letting x sub 0 equal the x value in the given point and y sub 0 equal y, the parametric equations, simply modeling after this, remember the general form is x sub 0 plus at for the x equation, so we get x equals 2 plus 3t. And y equals, in general form, y sub 0 plus bt. We get y sub 0, which is 1, from that point that the line's going through, plus 1t, or just t, for t between negative infinity and infinity. The line passes through 2, 1 when t equals 0 and rises to the right as t increases, as you can see here in the graph. Notice that the other choices for a and b also work. For example, a equals negative 6 and b equals negative 2. The equations are x equals 2 minus 6t and y equals 1 minus 2t. These equations describe the same line. All we've done is multiplied both a and b by a common constant, in this case negative 2. And that was that k factor we talked about at the end of the last definition. That if we multiply a and b by the same integer value, then we basically have the same line. Okay. The last one, notice we're given 2 points, and we want to find the parametric equation. So remember, we need x sub 0 and y sub 0, which are the starting point or our segments, so we can use the first point because it starts at 4, 7, and so that would be a good x sub 0 and y sub 0, 4 and 7. The other thing we need to write the parametric equations is a and b, and since we're given 2 points, we can find the slope of this line. The slope of the line is 7 minus negative 3, y2 minus y1, over x2 minus x1. Okay, and that gives us 5. Notice, however, that when the line segment is traversed from P to Q, x and y are both decreasing. To account for the direction in which the line segment is generated, because the slope is positive, but we're moving in a negative direction, they're both decreasing, we let both a and b equal negative numbers. So b would be negative 5, and a would be over negative 1. We could also do 5 over 1, but again, this kind of describes the behavior of the graph better. So then, as we said, 4, 7 is the starting point. We're going to use 4 and 7 for x sub 0 and y sub 0. And thus we get the two resulting parametric equations, 4 minus 1t, and x equals 4 minus t, and y equals 7 minus 5t, plugging in the values for a and b into the general parametric equations. Okay? Because the equations describe a line segment, not a general line that goes on to infinity, the interval for t must also be restricted. So what value of t corresponds to the endpoint of the line Q23? Like how long did it take us to get from this point to this point is what we're asking. So x equals 4 minus t equals 2, right? So we're setting the parametric equation equal to the endpoint of the x value. So we get x equals 4 minus t, that's the general form of the equation. And we're trying to figure out how long it takes to get from here to here, so we set it equal to the final x point. So notice that we get t equals 2. So we can see that this is our t equals 0 point, this is our t equals 2 point, so t has to be between 0 and 2. You could check this by using the y values as well. Next, let us look at how we can come up with parametric equations of curves with example 4. A common task is to parameterize curves given by either by Cartesian equations or by graphs. Find a parametric representation of the following curves. Part A, the segment of the parabola y equals 9 minus x squared for x between -1 and 3. When we have an equation like this, it's often easiest to substitute one of the variable values and set it equal to t. And in the case of part A, the simplest way to define this curve is to let x equal t, and then we have y as a function of t, where t is the parameter. We must then find the appropriate interval for the parameter. Using this approach, the curve y equals 9 minus x squared has the parametric representation x equals t. Therefore, y equals 9 minus t squared are parametric equations. And since x and t are equal, then the interval is going to be equal as well. And so t is between -1 and 3 as well, as you can see here. This representation is not unique. For example, you can verify that the parametric equations x equals 1 minus t would give us the parametric equation for y to be equal to 9 minus 1 minus t squared. But then notice if we do this, then our interval is going to shift. As x equals -1, then t would equal -2. And as x equals 3, then t would equal 2. But notice in this, actually it's the opposite way around, isn't it? As x equals 3, that gives us t equals -2. And as x equals -1, 1 minus -1 is +2. So notice what happens here when we define the interval. It actually kind of flip-flops direction, and so the equations then move from right to left instead of from left to right in this other form of the equations. Now let us think about B. We can do a similar thing with equation in B, x equals y minus 5 squared plus the square root of y. Because the x variable is determined by the y variable, it would be easier to do the substitution in reverse, specifically to make y equal to t. If we do that, then the parametric description of the curve is x equals t minus 5 squared plus the square root of t, and making y equal to t. Notice that t can take values only in the interval from 0 to infinity. Why is that? Because we're doing the square root of t. So as t goes to infinity, we see that x goes to infinity and y also goes to infinity. All right. So our t values in this case are more limited to define than all values between -infinity and infinity. The last case is a little bit more complicated. We have two lines that are connected through a piecewise linear path. Okay, so we go from point P to Q and from Q to R, where the parameter varies from 0 for T varies from 0 to 2. So this path, as I just mentioned, consists of two line segments. We go from P to Q and from Q to R. So we have the coordinates of these points, and we can find the slope of each of these to find b over a. The line segment PQ originates at negative 2, 0, so these are our x sub 0 and y sub 0 points, and unfolds in the positive x direction with a slope of 3 over 2, so b is 3 and a is 2. And so we have those two values, if you will. So we have negative 2 plus 2t equals, and y equals 3t for t between 0 and 1. Now finding the parametric equations for the other line is a little bit more difficult. We want the line segment to originate at Q03, right? But notice that at this point, t is equal to 1, okay? And end at point R, which is 4, 0, when t equals 2. Observe that when t equals 1, x equals 0, and when t equals 2, x equals 4. So substituting this pair of values into the general x equation, x equals x sub 0 plus at, we get these two following equations. X sub 0 plus a equals 0, and x sub 0 plus 2a equals 4. So we can use these two equations to find out, solving for x sub 0, we find that x sub 0 equals negative 4, and a equals 4. Applying a similar procedure to the general y equation, y equals y sub 0 plus bt, the relative conditions are y sub 0 plus b equals 3, and y sub 0 plus 2b equals 0, because y equals 0 and t equals 2. Solving for y sub 0 and b, we find that y sub 0 equals 6 and b equals negative 3. Putting it all together, the equations for the line segment QR, x equals negative 4 plus 4t, and y equals 6 minus 3t for t between 1 and 2. So while this first equation was simple because we were starting at the 0 point for t, the second one we had to adjust our values using the equation values and the relationship between t and x and t and y, and knowing that we're going from t equals 0 to 1 to 2. Okay, you can verify that the points Q and R correspond to t equals 1 and t equals 2 respectively. Furthermore, the slope of the line is b over a, which is for negative 3/4, which is correct as well, as you can look at these two equations. So this is another long lecture. We're about midpoint through, and this is a good breaking time. I suggest you grab a coffee, take a nap, do some break dancing, whatever you need to do to kind of refresh yourself, or possibly even finish the lecture for today and come back and start at this point tomorrow. Okay? Many fascinating curves are generated by points on rolling wheels. Examples 5 and 6 investigate two such curves. Example 5, rolling wheels. The path of a light on the rim of a wheel rolling on a flat surface. You can see the light here in the image to the right. We're trying to figure out where does that light go as the bike moves forward, and you can see the path here. Has the parametric equations x equals a times t minus sine t, and y equals a times 1 minus cosine t for t greater than or equal to 0. And the path of light on the rim of a wheel rolling on a flat surface is a cycloid. Okay, this is called a cycloid, where a is greater than 0. Using a graphing utility to graph the cycloid with a equal 1, on what interval does the parameter generate the first arc of the cycloid? If we graph the cycloid between 0 and 3 pi, you can see the graph below. The wheel completes one full revolution on an interval between 0 and 2 pi, which gives one arc of the cycloid as well. So the wheel will get all the way back to its beginning part exactly at 2 pi, because we're doing one complete revolution. Okay, and this gives one arc of the cycloid. Next, we look at derivatives and parametric equations. Parametric equations express a relationship between the variables x and y in terms of a third variable or parameter, typically t. Therefore, it makes sense to ask about dy dx, the rate of change of y with respect to x at a point on a parametric curve. Once we know how to compute dy dx, it can be used to determine slopes of lines tangent to the parametric curves. Consider the parametric equations x equals f of t and y equals g of t on an interval on which both f and g are differentiable. The chain rule relates the derivatives dy dt, dx dt, and dy dx as dy dt equals dy dx times dx dt, or the derivative of y with respect to t is equal to the derivative of y with respect to x times the derivative of x with respect to t. Provided that dx dt doesn't equal 0, we divide both sides of the equation by dx dt and solve for dy dx to obtain the following result. Let x equal f of t and y equal g of t, where f and g are differentiable on the interval ab. Then the slope of the line tangent to the curve at the point corresponding to t is dy dx, which notice is the derivative of y with respect to t, or g prime t, divided by the derivative of x with respect to time, dx dt, which is equal to f prime t. So if we can figure out those two parametric equations and take their derivative and then divide them, g of t divided by f of t, the y function parametric equation divided by the x derivative parametric equation, provided that the f prime doesn't equal 0. So let's see how we can do this in an example. So let's look at example 6, slopes of tangent lines, and recall from what we just learned that the derivative of y with respect to x is the derivative of y with respect to t over the derivative of x with respect to t, or the derivatives of each of our parametric equations in a ratio. Slopes of tangent lines, find dy dx for the following curves and interpret the result and determine the points, if any, at which the curve has a horizontal or vertical tangent line. Well, remember that the slope of a horizontal line is 0 and the slope of a vertical line is undefined. Okay, so if we're looking at this ratio, the slope will equal 0 when the numerator is 0, and the slope will be undefined when the denominator is 0. Okay? So notice here for part A, we have simple equations, x equals t and y equals 2 times the square root of t. These are both easy to take derivatives of, the parametric equations, to find out what our dy dx is. We find that f prime t, the derivative of t, is 1, and the derivative of g of t, or 2 times the square root of t, is 1 over the square root of t. So when we plug them into the definition of parametric curves, we get dy dx equals the derivative of g prime, 1 over the square root of t, over 1, which just gives us 1 over the square root of t, provided t does not equal 0. Notice that t dy dx does not equal 0 for t greater than 0. So the curve has no horizontal tangent lines. There's no way for us to make the numerator 0 because it's a constant there. On the other hand, as t goes to 0 from the positive direction, as t goes to to 0 from the pi, we see that dy dx goes to infinity. Therefore, the curve has a vertical tangent line at 0, 0, which we also can see that from this graph, because when the denominator goes to 0, we have an undefined tangent line, which would be at when t equals 0. Therefore, the curve has a vertical tangent line at 0, 0. To eliminate t from the parametric equations, we substitute t equals x into the y equation to find that y equals 2 times the square root of x. Because y is greater than or equal to 0, the curve is the upper half of a parabola that you can see over here to the right. Slopes of tangent lines at other points in the curve are found by substituting one corresponding values of t. For example, the point 4, 4 corresponds to t equals 4, and the slope of the tangent line at that point is 1 over the square root of 4, or 1/2, which is what we would apply anyway here, right? If we know that the derivative is 1 over the square root of t, then what is the derivative at 4, 4? Well, since x equals t, then we plug in the 4 and we get 1 over the square root of 4, or 1/2. Pretty straightforward using the formula from the definition that we saw before. In part B, we're going to do a similar thing and then interpret it, okay? So these parametric equations describe an ellipse that you can see in the green figure to the right. Specifically, x equals 4 cosine t and y equals 16 sine t for t between 0 and 2 pi. The ellipse has a major axis of length 32 on the y-axis and a minor axis of length 8 on the x-axis. In this case, the derivative of x, dx dt, is negative 4 sine t, and the derivative of y with respect to t is positive 16 cosine t, right? Therefore, when we plug them into the fraction, we get 16 cosine t over negative 4 sine t, which is equal to negative 4 cotangent t. I actually think it's easier to figure out the horizontal and vertical tangent lines by using the fraction here than cotangent. So you're asking, when does cosine equal 0? And then, of course, for the denominator, when you have a vertical asymptote, the denominator would equal 0, making it undefined, would be when sine equals 0. Well, when we sine equals 0 at 0, so dy dx is undefined at 0 and also at pi. So these are when we're on the x-axis, if you're thinking about it graphically from trigonometry. And here they do an application of this, but you're still going to see that the sign is going to 0, and as it's getting closer, this is going to infinity, and that's really what an asymptote is there. Consequently, a vertical tangent line occurs at the point corresponding to t equals 0, which is 4, 0. Okay? A similar argument shows that a vertical tangent line, 4, 0 is here, sorry. A similar argument shows that a vertical tangent line occurs at the point corresponding to t equals pi, which is on the other side, 180 degrees, or pi radians, which is negative 4, 0. When does cosine equal 0? That's when we get to 90 degrees, or 270, when we're hitting the y-axis, right? When we think about trigonometry again. And so these are values of pi over 2 and 3 pi over 2. And so we have horizontal axes there. So I think in general, when we did trigonometry, we understood the unit circle in terms of cosine and sine, cosine being x values and sine being y values, and also recognizing when those two functions were, what they were equal to around the unit circle. So to me, it would be much easier just to leave this as cosine t over negative 4 cosine t over sine t, and then use those values. Because most of us aren't familiar where exactly cotangent is 0 and where cotangent is undefined. Okay? This is also saying that you can plug in values and find slopes at other places. Once we have the formula for dy dx, we can always find the slope of those tangent lines. So I don't think that's a big major point here. So our last topic in 12.1 is arc length and how to determine it using parametric equations. There is a step-by-step derivation of how this formula comes about in the arc length section in chapter 12.1. You know, it's not a bad, I would say, 5-minute read, but the bottom line is the definition, as you see here on this slide. The arc length for curves defined by parametric equations. We know that x is defined by a function f of t, and y is defined by a function g of t, where their derivatives are continuous and the curve is transversed once for t between a and b. And this means that we don't have a circle, etc., where we have different values, etc. The arc length of the curve between f of a and g of a, and f of b and g of b, so these are the x and y values at a and the x and y values at b, is equal to the integral from a to b of the square root of the derivative of f prime t squared plus g prime t squared. And this is just using the Pythagorean theorem, as you can see in the above graph, to define this, arc length, where we are, using an approximation by building a right triangle, where you have rise over run, delta y over delta x, which is, again, can be defined in terms of the derivatives of y and the derivatives of x. Okay, so here's the formula you need as we're going to finish the last two examples in this section. So let's look at our first example, example 7, circumference of a circle. The circumference of a circle. Prove that the circumference of a circle of radius a is greater than 0 is 2 pi a. And so, of course, the circumference of a circle is the arc length all the way around, or 1 revolution. We know from example 2 in this lecture that a circle of radius a is described parametrically by x equals f of t, which equals a cosine t, and y equals g of t, which equals a sine of t for t between 0 and 2 pi. If we take the derivative of a cosine t, we get negative a sine t, and if we take the derivative of g of t, we get a cosine t. So we can find the circumference by using the arc length formula. L equals the integral from 0 to 2 pi of the square root of f prime t squared plus g prime t squared. So we simply substitute in those values for f prime and g prime. And notice that what we get here is sine squared t plus cosine squared t. And of course, sine squared t plus cosine squared t is equal to 1 by the Pythagorean theorem. And so we just get, and here when they got a squared, we pulled that out, factored that out as an a. The square root of a squared is a, and since it's a constant, you can put it outside of the integral, and therefore we get a times the integral from 0 to 2 pi, which of course is 2 pi minus 0 times a, or 2 pi a. So our last example, example 8, is an asteroid arc length. An asteroid is a hypocycloid with 4 cusps, like a square with concave sides. You see it in here. Kind of almost star-like quality, but a square with concave sides. Okay. We're still going to use our formula here for arc length, of course. Asteroid arc length. The path of a point on a circle A with radius a over 4 that rolls on the inside of circle B with radius a is an asteroid or a hypocycloid. its parametric equations are a cosine cubed t and y equals a sine cubed t for for t between 0 and 2 pi, 1 revolution around the circle, of course. Graph the asteroid with a equals 1 and find its equation in terms of x and y. Okay. So this is quite interesting, how to kind of do this. We have x equals a cosine cubed and y equals a sine cubed. And because sine and cosine both have a period of 2 pi, the complete curve is generated in 1 revolution around 2 pi radians. Okay? So to eliminate t from the parametric equations, they've done something clever here. So instead of trying to define t by taking the cube root of x, etc., which we sort of are doing that, we've got the value of a equals 1, so we just have x equals cosine cubed, etc. But instead of just taking the cube root and making this the cube root of x equals cosine t, they've decided to square that again, and so we get x to the 2/3 equals cosine squared t. Now there's a real solid reason for this, and it's again based on the Pythagorean theorem. And if we do the same thing for y, notice we get x to the 2/3 plus y to the 2/3 equals cosine squared plus sine squared, which of course equals 1 by the Pythagorean identity for in trigonometry. So by doing this, we have terms that we can add together and then substitute in a simple numerical value which eliminates the t's. So this is quite a clever, and it's a little bit tricky kind of solution to this problem. But when you notice that you have cosine cubed and sine cubed, that was a really clever way to solve that, to use the Pythagorean identity, where you could get rid of the cosine and the sine together by taking the cube root of each variable x and y in terms of its parametric measure and then squaring it. And so that's what this is here. X to the 2/3 is the cube root of x squared, which gives us cosine squared. So clever. These things you really have to be creative. You have to be thinking at different levels and, looking at what you have here and figuring out how to find an equation. This was a challenging one. I mean, it's really simple in some ways, but to come up with this idea is definitely an interesting challenge. Okay. So find the arc length of the asteroid with a equals 1. So we have our arc length formula here. One of the simplest things to do in trying to find this arc length, and instead of trying to find all of the arc lengths, all 4, we recognize that the arc length of the entire figure will be 4 times the figure, the arc length in quadrant 1. Okay, since this is a square with concave sides. So we know that x equals cosine cubed t and y equals sine cubed t, with a equaling to 1. So we need to find the derivatives of each of these terms. And we get the derivative of x, or f prime t, is -3 cosine squared t sine t, and this is using the chain rule. And similar for y, equals the derivative of y is 3 sine squared t cosine t, and again that's just using the chain rule from calculus 1. So now we can apply this in the integral. And again, what we're going to do is we're just going to find the measure in quadrant 1. So we're going from 0 to pi over 2, or 0 to 90 degrees. And we're going to multiply that times 4 on the outside so that we can find this length and then multiply it by 4 to get the total arc length. And so when we do that, we have this here. from 0 to pi over 2, 4 times the integral, the derivative of f of t squared and the derivative of g of t squared. So when we do -3 cosine squared t sine t squared, what this comes down to altogether is 9 cosine to the 4th power t sine squared t. This is all a product, so it's not a FOIL in here, it's simply a product, right? Raising the power on each. -3 squared is 9, cosine squared squared is cosine to the 4th, sine squared is sine squared. Similarly here, 3 squared, 9, sine squared squared is sine to the 4th, and cosine raised to a power 2 is cosine squared. All right. Notice we have a cosine squared and a sine squared in each. We also have a 9. Well, first of all, we can factor out a 9. So we have 9 times the sum, and of course, when a product inside of a radical, you can take the square root of each. So we have 3 on the outside. That takes care of the 9. And then notice we have a sine squared and a cosine squared in each. So if we factor out a sine squared and a cosine squared, we're left with cosine squared plus sine squared, which of course we can substitute in. This equals 1. So what we're left with is the square root of cosine squared times sine squared. Well, the square root of cosine squared is cosine. The square root of sine squared is sine. And 3 times 4 is 12. So now we just simply have to evaluate this over the integral from 0 to pi over 2. So if we let u equal sine t, then du equals cosine t, and notice what we have here is u du. Okay, now they've gone ahead and changed the values of the parameters instead of changing back. But when you evaluate this integral, you get 12 times the value of the integral between 0 and 1, right? These are the value of t. The sine of 0 is 0. The sine of pi over 2 is 1. So that's how we get the new limits of integration. And then when we evaluate this, you get what? God, I just went blank. 1 over 1/2 u squared. 1/2 u squared, 0 to 1. Okay. So you get 1/2 over 1, which is 1/2, and 12 times 1/2 is 6. So the length of the entire hypocycloid or asteroid is equal to 6. So this one was a little bit, you still had to do some critical thinking here. And one of the key points is recognizing that, that if we found the arc length of one side, then we can multiply that by 4 to get the entire arc length. You know, there were some other things to figure out, like the integration limits, 0 to pi over 2, because we're only doing that first quadrant, and then simplifying the radical from the formula. So this has been a long lecture as well, and hopefully you've made it through, and we'll move on to the next lecture.